The J-XDS fighter jet's design philosophy centers around maximizing performance, agility, and reliability by integrating two powerful engines paired with advanced 2D thrust vectoring capabilities. This combination influences almost every aspect of the aircraft's operational potential, from raw speed and maneuverability to survivability and mission versatility. Starting with the twin-engine setup, the presence of two engines rather than one is a significant factor in boosting overall thrust output. The two engines work either in tandem or independently, providing the pilot with increased power reserve. This means that during high-intensity combat maneuvers, such as rapid climbs, high-speed dashes, or sustained supersonic flight, the jet can rely on the additional thrust to maintain performance without compromising on fuel efficiency or endurance. The combined thrust from two engines also enables the J-XDS to carry heavier payloads, including larger missile loads, advanced sensor packages, and fuel tanks, without sacrificing speed or agility. This is particularly important for multirole fighters that must be adaptable to a variety of mission profiles, ranging from air superiority to strike missions. Another critical advantage of a twin-engine arrangement lies in its contribution to aircraft survivability. In combat conditions, damage to one engine does not necessarily mean the loss of the aircraft, as the second engine can sustain flight long enough to allow the pilot to either complete the mission or execute a safe return. This redundancy reduces the risk of catastrophic failure and increases mission success rates. Furthermore, having two engines allows for better thermal management and stress distribution during extreme maneuvers or extended supersonic flight, as each engine can be operated within optimal parameters rather than being pushed to maximum limits continuously. Coupled with the twin engines is the sophisticated 2D thrust vectoring technology. This system fundamentally changes the dynamics of flight control by allowing the direction of the engine's thrust to be altered within a two-dimensional plane, primarily up and down. This is typically achieved through movable nozzle flaps that redirect the jet exhaust, providing an additional force vector that the pilot can use to pitch the aircraft independently of aerodynamic surfaces. The benefits of 2D thrust vectoring are profound, especially in regimes where traditional control surfaces lose effectiveness. At high angles of attack or low speeds, airflow over wings and tail surfaces becomes turbulent and less effective at generating the necessary aerodynamic forces to maintain stable flight or execute sharp turns. By redirecting the engine thrust, the jet can maintain or even increase its pitch authority, allowing it to perform extreme maneuvers such as rapid climbs, tight loops, and sudden pitch changes that are essential in dogfighting or missile evasion scenarios. This vectoring capability also enables the J-XDS to perform controlled post-stall maneuvers, which can be decisive in close-range aerial engagements. Post-stall maneuvering refers to controlled flight beyond the normal stall angle where the wing loses lift. Normally, this would cause a loss of control, but with thrust vectoring, the aircraft can maintain control by using engine thrust direction to compensate for lost aerodynamic lift. This ability grants the J-XDS a unique tactical advantage, allowing it to outmaneuver opponents that rely solely on conventional aerodynamic controls. From an engineering standpoint, integrating 2D thrust vectoring requires careful design to ensure that the nozzle mechanisms can operate reliably under extreme thermal and mechanical stress. Jet engine exhaust gases can exceed temperatures of several thousand degrees Celsius and generate immense pressure and vibration. The movable nozzle flaps must be constructed from advanced heat-resistant materials and engineered to move quickly and precisely without sacrificing structural integrity. This precision is critical because any delay or error in nozzle positioning could destabilize the aircraft or reduce the effectiveness of the maneuver. The flight control system of the J-XDS is another critical piece of the puzzle. Modern fighters rely heavily on computerized flight control systems, often referred to as fly-by-wire, where pilot inputs are translated into electronic signals processed by onboard computers that manage control surfaces and thrust vectoring nozzles in real time. For a twin-engine, thrust vectoring aircraft, the flight control software must coordinate the movements of two separate vectoring nozzles in conjunction with traditional aerodynamic controls like elevators, rudders, and ailerons. This coordination is complex but necessary to provide smooth and responsive handling across all flight conditions, from low-speed loitering to supersonic dash. Moreover, the combination of twin engines and thrust vectoring positively impacts the aircraft's supercruise capability. Supercruise is the ability to fly at sustained supersonic speeds without relying on afterburners, which are fuel-intensive and increase infrared signature, making the aircraft more detectable by enemy sensors. Having two engines with sufficient thrust margin allows the J-XDS to maintain high-speed cruise efficiently, reducing fuel consumption during transit and increasing the time it can spend on station or in combat. The maneuverability afforded by thrust vectoring also enhances the jet's survivability against modern threats. With the growing prevalence of highly maneuverable air-to-air missiles, an aircraft's ability to rapidly change velocity vectors and orientations is crucial for missile evasion. The thrust vectoring system allows for abrupt changes in pitch and rapid deceleration or acceleration, making the J-XDS a challenging target. In operational terms, the twin-engine, thrust-vectoring J-XDS can also operate from shorter or less prepared runways. Thrust vectoring can supplement aerodynamic lift during takeoff and landing phases, reducing the runway length needed and allowing for greater operational flexibility. This capability is particularly valuable for deployments in austere environments or from expeditionary airfields where infrastructure is limited. The twin-engine configuration combined with advanced 2D thrust vectoring gives the J-XDS significant advantages in power, agility, control, and survivability. It allows the aircraft to perform a wide range of demanding aerial maneuvers, operate efficiently at supersonic speeds, and remain effective even under adverse combat conditions. The integration of these technologies represents a modern and sophisticated approach to fighter design, ensuring that the J-XDS can meet the complex demands of modern air combat.